Okay, and we are recording. So, welcome, lecture 11. Transformers and evolution of LLMs. So why, transformers, everybody knows now what transformers are and why they are important. Why evolution of large language models? Well, we're not doing archaeology of NLP, not yet. But I guess it's important to understand why things are how they are these days. Like why ChatGPT is such a successful model, and why others are competing, and what preceded that, and how fast actually it all went, and why it works. How it works, and a little bit of why. So the last lecture we discussed, just a reminder, we discussed the GPT, and the decoder-only models. And I'm not sure we mentioned what GPT stands for. I haven't really double-checked it, but I believe, this is like from my memory, it stands for General Pre-trained Transformer. Can someone fact-check it, like Wikipedia, if this is correct? I guess so, but actually I'm not like 100% sure. Generative. Generative. Yeah, because they generate tokens. So decoder-only models, generative pre-trained transformer. It doesn't matter, but you can sound smart in the bar. Somebody asks about ChatGPT. What is ChatGPT? What it stands for? Well, I have no idea. Okay, good. So that's what we talked last lecture, and we basically talk about the architecture. So basically, what makes GPT a model? Why does it work? And we spend quite a big deal on talking about this causal self-attention. So the attention mask in decoder transformer, and why is it important? Because we have to look into the back, and we cannot foresee the future, as opposed to the BERT model, which was the encoder, where you take the whole sequence. And you can look, from every token, you can look back, you can look to the future. It doesn't matter because you're encoding the whole sequence. So this is where we are. And let's have a look where it all started, by the way. So there was this very famous, I think like one of the most cited papers in AI these days, I would say. This very famous paper called Attention is All You Need. And it has been many times refurbished into something is all you need, and everybody's claiming that now we have something which everybody needs for doing AI, and it's not anymore attention. So there's papers like attention is not anymore all you need and stuff like this. People are making fun of this, of research a little bit. But attention is all you need basically introduced the transformer architecture back in 2017. So it's being done by a couple of very, very smart people at Google Brain, University of Toronto, Google Research, and others. And let's talk about this first, because it's important to understand why we ended up with BERT and why we ended up with GPT, then with decoder, why the encoder-decoder actually, where it comes from. So we know now that the encoder transformer is the roughly the BERT model. So again, it takes the whole sequence, goes through the transformer layers, and output a sequence of embeddings for each token. And then we have the decoder, which takes a sequence, goes through the whole sequence, when generating next token, goes through all the sequence, learns the embeddings, and then tries to predict what the next word could be based on the all these embeddings. Or the last one. So, and then predicts the next word. So, okay, what could that be helpful for? Or where does it start? It's this architecture. It's the encoder-decoder transformer. So this comes from is it readable a little bit somehow? Okay, good. So this is the famous picture everybody's using all over the place. If you start looking for, explaining transformer, this is the picture from the paper. So now that we know how the architecture works, because we spent one lecture on BERT and one lecture on GPT, this shouldn't be anything. Nothing here should be surprising. So let's have a look and a little bit dissect here, because we know it already. So basically the main idea is that we can split this into two parts, roughly. So, the semantics of the arrows and the boxes differs from one depiction to another depiction. But roughly here we have the encoder, and here we have the decoder, roughly. And the idea of the encoder is the same as in the BERT transformer encoder and others, is we take the inputs and, okay, let's go through this architecture, and we see there's nothing new. So we have the input embeddings and we have the positional embeddings. Yeah, of course, we talked about them already. Okay, good. So we sum them up. Oh, sounds good, sounds familiar. Then we have n times this encoder transformer head. Oh, is it head? No, layer. It's a transformer layer. And of course, we had it also in our kind of understanding. So there's a couple of layers because the deeper we go, the better. And we're talking about 12 to 24 layers in BERT, 12 layers, I guess. So this is what it stands for. It's repeated. And then what is in here is the multi-head attention. Okay, so we know what's in there. Multi-head attention, query key and value, scaling, dot product, and softmaxing, and all these things in the multi-head attention. And here we have again the residual connections, so add and norm. And then what is in here is again one path goes directly through, and the other is this feed-forward network. Okay, so this is basically the BERT model. Okay. I mean, it's just depicted differently. And of course, we talk about this like the ordering of normalization, of layer normalization is a little bit different for different models. So in some models, it's before the attention and before the feed forward. In the original models, after the feed forward and after the attention. And the reasons for that are kind of, I would say, empirical. I don't know whether there's strong like theoretical reasons. So people maybe tried and it worked better. Like most of the things in NLP, just there's some intuition and then you try and it works. Okay, so this would be the encoder. And then we have the decoder, which is again, so we have the output embeddings and positional encoding. Again, we have again this self-attention and normalization. And then, okay, here comes the difference. So, okay, we have the feed forward here. You don't see, by the way, why don't you see this thing? Now, okay, sorry. Now we have also the multi-head attention. Okay, sorry, we had the feed forward thing, so it's the same. And now looking in the multi-head attention, okay, wow, that's interesting because now we have a difference from the standard GPT decoder only, because there is something coming out from the encoder. And this is exactly where, so we have three arrows here. So we have K, Q, and V, and they are in the standard BERT model or the GPT model, they are all from the same input. So the key query, if you remember, we have the X input and there were three arrows. And basically this is the same input, self-attention in a way. It's called self-attention. Here in the encoder-decoder, we have a thing called, I would say cross-attention, they call that it? Cross-attention. Where part of these things are coming from the encoder and part of these things is coming from the decoder. And then they will be combined in the attention head. So let's have a look exactly what they were doing here, because the rest is then just standard linear softmax, projecting into the vocabulary or into the token inventory, because you want to generate tokens. And there's some linear projection as well. So the rest is kind of the same as we discussed. But here the cross attention is a different thing, and it was in the original paper. And so the queries come from the previous decoder layer. Okay, so now we are in the decoder. The queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. Okay, so this is it. This is where we combine key, query, and value. So what was it again? Keys and values. So keys and values are coming from the encoder here, while the query is coming from the decoder. It's one way of combining these things. So what could be the intuition for this? That every position in the decoder to attend over all positions in the input sequence. So this is the motivation why this cross-attention is important. What does it mean is, so imagine the task they were actually testing on was machine translation. So, and there was also historical reason why attention or cross-attention was popular or important in machine translation. The main reasoning behind, or the main idea behind is that you have your input sequence, tokens, in one language, and then you start decoding in another language. We could do this with LSTMs, for example. LSTM, you input, you have the all encoder input, and then you start decoding in LSTM as well. So this is the same mechanism. And at every token you are decoding, you're choosing now like, oh, which word should I choose now, like to generate next? I generated, so for example, could be, give me an example of a translation of German English translation. Okay, what could be the good example of that? Something. Okay, so where some past tense in German where you have the verb at the end. Okay, ich hab's gelesen. Oder ich hab blah 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 gelesen. Ich hab's gestern gelesen. Which means the verb is at the end, and there is hab and then so on. So, and then you start generating the English translation, and the English translation was like, well, I read this yesterday. Maybe I read it yesterday. So you are, okay, now I need to switch languages. Okay, so you are in the first position and try to generate a second, which I read. And for the read, you want to look into a couple of tokens which are important for you in the sequence, in the input sequence. So which tokens are important now? Not the entire sequence. You should pay attention to the second word and the second token and the last token. Ich hab blah 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 gelesen. Because these two words will tell you that you have to put the read in the past tense in the English translation, and the model should basically learn this. So it should attend to the verbs, and it could be split across the sequence in the second position. After generating this, I read it. So then you go back to maybe your third token, and so you get a gist. Basically, the model can learn to attend to particular tokens from the input, and should have access to all the tokens from the input because they play a role at a certain output. And for example, this verb, why is it? Okay, so the question is like, why German language works like that? I have no idea. I know why. I always say like German people are very patient because they wait for the most important part of the sentence is really at the end. And that's my explanation why people wait for the green light on the street, across the street. This is my explanation. There's patience, basically. You can wait until the green light comes where there's no cars in there, but you just wait for green and just pass by. It's like waiting for the verb at the end of the sentence. I'm trying to learn this hard. Okay. Jokes apart. So this is how the attention has access to all the tokens, and this is motivation. And it worked also with LSTM. So there were papers 2015. One of the first papers which introduced attention for machine translation using LSTMs. So similar principle, but not using the transformer. Okay, so it mimics the typical encoder-decoder attention sequence-to-sequence models. That's what I just said. Okay, it's even written. So does it make sense? Why this is important for machine translation? It could be important for many other things, but it turned out to be very important for machine translation. Okay, so this is the original, this is it, encoder-decoder. So now the question is like, why? And okay, so no, let's go back to the paper because I might have here a couple of notes here. The transformer uses multi-attention in 3 different ways. The encoder contains self-attention layers. So in self-attention layers, all of the keys, values, and queries come from the same place. Okay, so this is the BERT model. Everything is the input, and you just have the Q, key, and V from the same input, but you do it across self-attention. Output of the previous layer in the encoder. Each position in the encoder can attend to all positions in previous layer of the encoder. Okay, so we know this already. This is the BERT model. Okay. Well, this is basically before BERT model. This is what the BERT model basically took from, just the encoder, because you want to just encode the sequence for doing mostly text classification. Then in the decoder self-attention, they allow each position in the decoder to attend to all positions in the decoder, up to including the position. So this is basically the causal mask, of course, because if you're decoding the sequence, you want to also know like what you decoded before, like the previous words, for example, I read, ate. You want to know what you decoded already, so to generate the next word yesterday, for example. And including everything in the encoder also. So we need to prevent leftward information flow. So basically this is quoting from the original paper, so this is a research paper in a way. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside a scale. Okay, so that's what I did. We implement this inside a scale.product attention by masking out That's what they did. All values in the input of the softmax which correspond to illegal connections. This is our mask we talked in the last lecture. So you mask everything. They call it illegal connection. This is like cheating, looking into the future. So you mask it with minus infinity. Because after softmaxing, it will become what? After softmaxing minus infinity, what you get? 0. Okay, yes, 0. Okay, so this is it. This is the transformer. And now let's come into the task. So as I said, like they tried it on machine translation. So, and we talk about different tasks of NLP, including machine translation, back in lecture 1. So you might remember, or you might want to recall that this WMT is workshop on machine translation. So WMT is the standard data sets for machine translation, English-German data sets. So it is like 4.5 million sentence pairs. And okay, so this is a standard task, or was standard task back in the 2017 for machine translation, standard competition. Why does it mean standard task? Means like if you are doing anything in machine translation, you have to have this data set in your paper just to compare to the others. You don't have to just make up your own data set and say like, well, I have the best system on the world. The reviewers will just kind of kill you and say like, okay, but by the way, here's a WMT14. How's your results? And it's like, oh, I don't know. Okay, reject. So of course you want to keep it in mind if you do research. Even if you don't, take the standard data sets first. Sentence. Okay, so this is the standard. This is the task, and sentences were encoded using byte pair encoding. Okay, so we know what it is. This is subtoken. Well, one of the methods for subtoken units. Byte pair. Then we have sentence piece and others. So you have not words but subwords, which has a shared source target vocabulary of about 37,000 tokens. Yeah, okay, so this is interesting. Why? Well, because you have, if you create your byte token byte pair encoding, if you do it in 2 languages, you want to have it created from both languages, because then you have just one single vocabulary in a way, or token inventory, both for the input and for the output, which is an advantage. So you don't have to have 2 kind of vocabularies, one in German and one in English. Basically, you have all your subword units in both languages, which might be kind of helpful or not. I mean, it turned out to be helpful. So for English French, we use a larger, okay, 30, so lots of data. Well, back then. So this is what they did. So there is nothing in this task. There is nothing about pre-training. So they didn't do any pre-training of this model as we were talking before, like the masked language, so the mask token pre-training of BERT, or the next BERT prediction of GPT pre-training. There is no pre-training. So what they did was basically take the model, initialize the weights randomly as usual, and then just train it on this task. No pre-training, just train it on machine translation. Okay, so this is what they did. And guess what? It was better than anything else on the market back then, more or less. So, okay. What is this? What is this? What is blue? Okay, so blue is one metric for machine translation. It roughly corresponds, if I'm not mistaken, it corresponds to the overall. So it's token overlap between your generated translation and the references, and it's corpus-based metrics. The lower, the better. No, sorry. Excuse me. It's the higher, the better. The lower, the better is for something else. Perplexity. The higher blue, the better, and it corresponds roughly to precision. So how many of the tokens were kind of right? You generate or token n-grams. So the higher, the better. The blue scores. And what they get from the transformer, from the big one, of course, I mean, they tried 2 different versions of the transformer, base model and big model. The difference was, I guess, just the number of the transformer layers. So the bigger the model, the more parameters, the more it can kind of ingest. And the differences were, okay, 28, 4. And then, well, you might be asking, is it good? Like, okay, 26 and 23, like, how big the difference is? Like 28 blue score, is it better or not? So in the neural machine translation community, like one point blue score up is actually already very good. It's significantly better, or significantly, not statistically, but somehow like perceived significant. So it's better. So 1 blue score up is good. 2 blue scores up just on the same task. So they didn't use anything extra. Just another architecture on the same train def test data, and you get like 2 blue scores up. So, well, it's kind of amazing, or was amazing. On English German, English French, okay, so on par with the others. Interesting. So, might have been back then like, okay, here's a new machine translation. Yes, you have a question. So the range of it's, I guess it's like 0 to 100. Yeah, it's a percentage. It's typically multiplied by 100, so it should be like 0.284%, something like that. No, it's 28.4% anyway. Yes, and it has some. So the higher the better, but you also don't want to have it like 100% because then basically it means like you generate exactly one text and you want some variance in your model as well. So there's no like what could be the best blue scores. Shouldn't be 0. It should be something like these numbers. So it's really relative. You have to. That's the trickiness of evaluating machine translation because this is just one blue score is kind of bad in a way, but it's a baseline metric. Okay, so any questions? So this was the original transformer. You know it already. The question is like, is it still relevant? Well, not as it is. I mean, I don't think this is still so much used, like the encoder-decoder architecture, as opposed to just encoder or just as opposed to as decoder. Why would you think so? Why do you think this is not used anymore? Or what's the disadvantages of this of such a model? What could be the big disadvantage of this model? So we have BERT, so just encoder model. We have GPT, just the decoder model, and now we have encoder-decoder model here, both together. What is the big disadvantage of having this thing? A practical disadvantage in a way. Yes? Yeah, it's bigger. It has just much more parameters. It has the double number of parameters because the parameters here in the encoder are different from the parameters here in the decoder. So all these things here in the attention, all these projections for Q, K, and V, all these projections for all these weight matrices for feed forward, all the matrices for, well, basically these are the biggest ones, are just doubled here, or well, even more, because you can have different number of layers in both, theoretically. So you need just much more parameters. So your model is at least twice as big. So what does it mean? You need twice as bigger GPU, or you need just twice as many GPUs? So performance in a way, like it's just too big. And if you have a model which is just half as big as this one, and can get similar results after training, then you take the smaller model because it's cheaper. So this is, I guess, one of the disadvantages. Why people then decided, okay, maybe you know what, maybe we don't need the encoder, and let's just take everything as just text generation. Before we go to that, so this is the GPT kind of family models. Let's spend some thinking about a shift in thinking in NLP, roughly around, let's say, 2020. Any question to the transformer? Okay, so attention is all you need. Maybe, who knows? The jury is out, but these days, yes, GPT models just rule the world. So here's the thinking, and I think we spent it. I think I talked about it a little bit in one of the first introductory lecture. So every task is a text-to-text task. So this is let's have a look what it means. So there is one model which nowadays it's not really important use. Maybe some use that for some multilingual T5 model, or I guess MT5 is still used in some contexts. The thing is why, so it was done by Colin Raphael and others who were also part of, what was that, part of the GPT, I think, like, no, I don't know. I mean, this very famous people, Google and others. So T5, the basic idea underlying their work is to treat every text processing problem as text-to-text problem. For example, which means taking text as input and producing new text as output. Well, it sounds kind of, sure, yeah, of course, makes sense. You just type in text and text comes out. But it's kind of, well, now it's because now we know it works. But back then, like, yeah, I mean, people were trying things. So what does it mean as an example? So the example is that, I mean, the standard tasks in NLP, for example, machine translation is text to text, of course. So here what we have as the input is, well, not only that you say, oh, that is good, that's good, but you also, because this is what you would have in the standard WMT data set, something like that. You would have the input sentence and the output sentence, and you know you are doing machine translation. So you don't have to say anything of those. So this is what this paper did, like train on sequence in, sequence out. And this is just machine translation. What I did here is, well, we can actually tell the model what to do, which task to do, by prepending the task description as text itself to the input. So we would say translate English to German and then put the input. Okay, why would you do that? Because then you can take the other task. For example, what is this? STSB. I think this is semantic text. Well, what is this STSB? Some similarity score. STSB stands for semantic similarity something, I hope. Let me just have a look at the example. Sentence 1, the rhino grazed on the grass. Sentence 2, a rhino is grazing in a field. Okay, so it's something about similarity of these two sentences. And you should give score how these two sentences are similar to each other. And here we have the gold standard answer would be 3.8. Okay, so what is this task now? It's not a classification. So this was generation. Generation is this task. This one is, what is this? This is a, how do we call a task where you predict a number? From statistics, actually. How do you, I mean, if you're a statistician, yes. It's a regression, exactly. It's just a regression. So typically in regression, in statistics, you have some input features and you predict a number. Could be typically like unbounded, bounded, whatever, but you just predict a number. In classification, you predict a class, label, or softmax probabilities. So you do regression, and here's this interesting thing. So you say here's the sort of the prompt or the task description or the instructions. What you should do. So STSB, sentence 1, sentence 2, you somehow frame the problem, describe the problem as a text. And this is coming out, obviously not as a number, but as a text. So you generate a token, 3.8, which actually has the meaning of 3.8 in the regression. Right? If you'd have like do standard machine learning regression, your function is outputting real numbers. Well, there is no function. I mean, transformers, they don't output any real functions, real value functions. Or sorry, they do not output real values. They output tokens. They can generate tokens. So here it means the model learns that it has to predict token, which has the meaning of the value which has to be predicted. It's very cool actually. It's very cool because the model has to understand something about numbers. It has to understand that maybe like 3.8 is smaller than 3.9 or 4.2, and then at the same time understand, oh, the similarity between these two sentences is a number which corresponds to this token. So I found it super cool. We have other tasks here, like classification. So the course is jumping well. I think this is a binary. I think this was a binary task of saying whether the sentence makes sense or not. And I guess the jumping well is kind of a not acceptable English sentence. So it would be like the label not acceptable. So it would be, I think it's like binary classification. And again, in binary classification, if you think about what was that? Some sort of small model with sigmoid at the end. So we would have 1 or 0. Now, instead of 1 and 0, we're getting the label name, like not acceptable and acceptable. So again, the model is generating a token which has a meaning of the 1 or 0, or the prediction or the label. So this is interesting because everything is now text. Predicting real numbers is predicting text, predicting labels is predicting text, and then obviously like text generation is text. Here was the machine translation, and this one is summarization, so summarize. summarization. So you just shorten the sentence and just rewrite it. So why this is interesting? Well, the point is you can train everything in one single model. So you can, if we come back to multitask learning, we just train the model on very many different tasks. First, so many different tasks. And second, we unify these tasks by prepending the task description to the input. So we're saying, oh, this is a translation task. Dear model, this is a translation task. Translate English to German, and then you put the input, and you should predict the output. So, and this is like unified API, text in, text out. It's just a text transformation, so transformer. Okay, any questions? I mean, makes sense now because we are using it on a daily basis in ChatGPT. Like, can you do, like what ChatGPT is doing is text in, text out. It's pretending it's output. Oh, it's not pretending it's outputting numbers. It's outputting numbers, but as tokens, not as like numbers. Okay, so T5 was kind of, they tried to investigate it much deeper in different setups. So what they did here is here they start pre-training the model. So you can pre-train the model, and back in the 2020, it was already known that if you pre-train the model, it will help for the downstream task. So they try different. What is here interesting? Like different. Can you read this? Okay, because I can't. It's very small. So prefix language. So there's some language modeling, bird style modeling, and other some sort of masking. So here's an example of how we do that. Thank you. So the language modeling would be thank you for inviting, and the target should be me to your party next week. So predicting, the rest of the sentence. The bird style modeling would be thank you, mask me to your party, then shuffled bird, week. And then it should reconstruct the original text, thank you for inviting me to your party last week. So Apple is kind of like the random shuffled bird. Okay. So this is what they try to pre-train the model on. And of course, so what do you pre-train your model? If you need text data, what do you pre-train on? Like where do you take your text data if you want to pre-train a language model? So if I ask you, like, can you pre-train your language model? I give you all the GPUs, but you have to take care of the data. Where do you get it? Any solutions? Wikipedia? Okay, good one. Is it good enough? Is it big enough? So how many tokens are in the Wikipedia? Well, I don't know. I mean, okay. I think 3 billion tokens could be in English Wikipedia, something like that. It will be in one of those tables later, maybe. So we'll double check. So okay, Wikipedia good. So more. It's not enough. More. IMDb small. More. Where do you get the data? Yes. Oh, there's a dataset pile. Okay, the pile is here since 2022. So let's pretend we're 2020. I want data. There's no pile. Pile is a good one. I mean, these days you would take pile, but it's based on something, by the way. Do you know what it's based on? What is in pile? Okay, so where do you get the data? What's the source? Social media. I mean, if you were Facebook, you have lots of data. Do you want to train a language model on that? That's a different question. I think you, of course, you will. But let's say you're a researcher at Ruhr. You're a master's student, and I'm going to tell you, like, okay, your task. The first one is just pre-train language model and then do some fancy stuff. Yes? Some articles on the internet. Is it enough? I mean, we have Wikipedia, we have IMDb, we have some articles, yes? Books? Free books. Free books is good. So book corpus, okay, we're getting somewhere. So I want more. The solution is much easier than you think. I want more. Can you give me more? What is more than those things? It doesn't have to be like one single data set, just data. How about the internet? No, seriously, like, how about the internet? Because the internet has Wikipedia, IMDb, articles, yes? Say again? The random thing would be internet? Yeah, of course. I mean, it's like it could be. It's so okay. That's a check. I mean, that's a catch. So internet could be anything. We want language data, right? We want train on language. We have language in Wikipedia, mostly language. We have language in IMDb, mostly language. We have in articles, it's language. We have, yeah, okay, these are good sources, but small. Then we have the internet. The question is like, how do you get the internet? So can you get the internet? If I ask you like, can you download me the internet? Can you crawl the internet? Yes, you can. You can crawl the internet. And it's not big. And it's called Common Crawl. It's there. You can download the internet. It's a couple of terabytes. If you just clean the text, it's a couple of gigabytes, like terabytes. I don't know, 30 teras, 100 terabytes. It's not big. Or even gigs. It's actually much smaller than you think. And somebody's doing it for you. You don't have to crawl the internet. Never crawl the internet at university. Never try this, because there's consequences. Because if you do this, university has access to many things which normal people have no access to. For example, journals and libraries. And if you start crawling them without noticing, they will kill you. So it happened to me. Never do this. Okay, so there's Common Crawl, which is a non-profit organization somewhere in the US since I don't know, something like, so you know, like the webarchive.org. So they're doing archival things. It's like non-profit for reasons, and you don't have access to their data unless you, I mean, maybe you have, or it's kind of complicated. So I don't know if you can download the archive. I've heard of people having a bigger European project partnering with Archive to get the internet from Archive. Common Crawl is downloading the internet every month since 11-ish, something. And that's it. You can just download it. It's hosted on AWS S3, and of course, you need storage, faster internet, and things like that. So, you know, but you can download the internet or from them, just get a crawl. So it's publicly available web archive that provides web extracted text. So basically, they're running on the. Did you do any scraping of the internet? Did you scrape any sites? What did you use? Which tools? Yeah.
Like predictions on to scrape some data from the, let's say,
Yeah. Okay. So how you typically scrape the internet is you need some. It's basically a crawler. So you need some seed URLs. And then you download all the HTML, parse the HTML, get the links, and put it into your kind of list to be crawled, and you iteratively crawl this. And there's tools to do so. One of them is Apache Nutch, N-U-T-C-H, and they're using Apache Nutch. It's been here for 20 years. It's like the not state-of-the-art crawler, but it's been used, and you can scale it up, and it's super huge. And basically, everybody can use this. You can really crawl the internet. You can crawl sites, but don't do this. So. And extract the text, so it produces around 20 terabytes of scraped text data each month. Unfortunately, the majority of the resulting text is not natural language. Surprise, surprise, internet is bad. Internet data is it's a mess. So you have 20 terabytes of something which is text, but it's not natural language. So if you just train on this, your large language model, there was a saying, how was that? Crap in, crap out, something like that. Yeah, something like that. So you don't want to do this. So what they do in this T5 paper is to clean it. So they call this colossal clean common crawl corpus, and it's small. If you clean up the internet, you put this on your hard drive. You have the internet in text on your hard drive. It's not much. It's like 1 terabyte. Now it's maybe bigger, but not really. Who knows? So what they did here is use some heuristics for cleaning common crawl. So, for example, discarded pages with fewer than 5 sentences because it's useless. Remove dirty words, naughty, obscene words. Okay. Many scrape warning setting. Okay. So the point is, if you scrape the internet without JavaScript, then the pages will just kind of will be unhappy that you don't have JavaScript. So you don't want your corpus full of, oh, your JavaScript is disabled, because Notch doesn't support JavaScript. And it's actually kind of hard because these days you have lots of pages that are just JavaScript only. And there's no, I'm not aware of any like out-of-box solution for crawling JavaScript websites unless you have Selenium, if you ever do something like that. So, but doing this on scale, on web scale with Selenium, I don't know. I guess like Google is doing that in scraping. Like Google crawler is actually crawling everything, and I'm pretty sure they have like JavaScript interpreter in there. In Common Crawl, they don't. So you have to get rid of those things. You want to get rid of lorem ipsum. Yes, you have a question.
Does that imply they also got rid of, for example, textbooks about JavaScript?
No, I think they, JavaScript should be enabled or something like that. So some heuristics. I would say like a couple of regular expressions, and then just remove this. I mean, if you get rid of a couple of books, it at the end of the day doesn't really matter on this scale. So you want to be more. I mean, it's a trade-off being like huge amount of data or high quality data, and you have to set up the trade-off. And they did it heuristically, saying like, okay, we're removing this and that, but this is not like, a principled approach. This is somehow hacking this, but makes sense for cleaning up the data. Okay. Lorem ipsum, yeah, unless you want to train lorem ipsum generator. Code, of course. So here's an interesting thing. Of course, lots of internet has a code, like the entire Stack Overflow is full of code. They decided here not to include code in there, all the GitHub. Like you don't want to train on GitHub. But it turned out later, actually, you Copilot, you train on GitHub. You train specifically LLMs for code generation, code understanding. So then you just clean just the code. Here they train on language only. So they get rid of code, but it was a design choice. And they duplicated the set. Okay, so if there's a one-to-one duplicates, they discarded duplicates. So it's a lot of work. It's great somebody does it for you, so you don't have to repeat it. And I think Pile is based on this C4 corpus, if I'm not mistaken, or something like that. I mean, Common Crawl is absolutely part of Pile because there is no other freely publicly big data set these days than Common Crawl. And the advantage of Common Crawl is actually you can really get the crawls from every month from the last 10 years. There will be duplicates, but it's a lot of data because they don't crawl the same pages every month. There's some randomness in there. There's new seeds. The internet is growing, so they don't just refresh it. Yes.
Not everything is HTML. I mean, lots of stuff is PDF.
Yeah. I'm sorry. So I think in Common Crawl they don't crawl any. Wow. That's a good question. So I don't think they're crawling PDFs and documents. I don't think so, but maybe you can double check that. Maybe. I mean, if you have PDFs, that's a different story. You need to extract it, and PDFs are just horrible, like for text. So I mean, they're great for printing, but horrible for extracting text. So I think they just you just discard it because there's more text just freely available.
You can transfer any PDF into any format, right? Online. Like,
Yeah, but can you automate it on like terabytes of data? That's a question. I don't know either. I mean, if you can make it, if I give you like terabytes of PDFs and you in 2 hours you give me clean text because it's extracted automatically, then maybe it's worth trying. So basically, everything is like you can spend years on cleaning up the internet, but this is not your primary goal. Your primary goal is to have language data of some good quality to train your language model. Yeah, just plain text. You're asking why? Or why is it so difficult to get data? Yeah. Why is it so difficult? Well, I don't know. I mean, so PDFs are difficult because it's like, have you tried to extract text from PDFs like of different formats? It's bad. So you better say like, I don't want to waste time and make like ad hoc, make a solution for PDFs because maybe it's just, it's not worth the effort now because I have other, gigabytes of text here freely available as plain text, as raw text. It's a trade-off and design decision. Like that's what motivated them to do so. Some heuristics. If you're I believe like if you say like I'm interested in cleaning the internet or I want to do no seriously like I want to do like data cleaning or data preparation for language models, like you get like job offers right away because everybody wants to train on this data. So okay. So they train on this 750 gigabytes. They train different models, all these different sizes. Well, this is small now, but it's sort of readable. Anyway, so different sizes of the models. So base, large, 3 billion parameters, 11 billion parameters, and different data, different downstream tasks, and so on. So here's the bitter lesson. And we can call it the bitter lesson. This is it. The scale of the model matters. Just if you make it bigger, nothing else is important. If you train it on, for example, here, they try the different objectives like bird style, GPT style, different masking and stuff like that. All these kind of different combinations, they really tried. Nothing matters if you just make a model bigger. Just make a bigger model and nothing matters. And there is, if you look up on the internet, the bitter lesson, you will find an article from Suttner, I guess is his name, like computer scientist, basically claiming that in the past 50 years, in everything in computer science, everything we kind of do will vanish when you get better compute or bigger compute. Just get more powerful computers. And everything which you designed before is obsolete because the scale matters. If you can scale it up, no matter what kind of cool techniques you had, cool architectures, if you can scale it up, you will get better performance. And the same is for LLMs. It's kind of really bitter. Like doing research in LLMs, kind of like, I have this cool idea, so let's try this kind of self-attention, and now we can do this masking new and blah, and all these, and I do experiments, and I get a little bit better on blue score here on this data set, and so like paper. And half a year later, one of these big techs comes with a GPT-4, and they train it on twice as big GPT model and 7 times big as the internet, and everything is forgotten, like because this is just better results. Scale matters. If you can scale it up, and it's kind of tricky. We don't know how to do. We don't know, like the research community, we don't really know how to do this properly. How can we reason about scaling? What is coming? Like how do we get enough data first? Like can we scale to infinity? No. The internet is limited in the size. So there are sayings like, oh, we're running out of words, like tokens. We're running out of tokens. Like in 2 years, we'd have nothing to train on. For one reason, well, we reach the maximum capacity of these models, and the models will be bigger, and our compute is bigger, but then we don't have the data to fit in. And second, most of the internet will be GPT generated anyway. Like nothing will be written by humans. So we'll be training, and there's the research, what happens in the limit if you train off self-generated data, how the quality will decrease and will kind of be vanish to something unusable, sort of. So there's even theoretical research on it. By the way, this lecture is really like a sort of contemporary elements, so more like research oriented. So I don't, this is more like, if you want to do research, this is what people are dealing with. So I don't want you to, learn any of those because it will change somehow soon. But the bitter lesson will stay here, like scale matters most. So T5 was cool for this reason, like everything is text to text. And since then, I'm kind of, it's stick. So everything is text. In GPT, everything is text. Text in, text out. Unless you do like multimodal models where you have images and text. And they can generate, and there you have models for image generation, which are kind of different architecture. So these diffusion models. And we don't talk about it. So, but NLP, text in, text out is the paradigm. And the scale matters. Okay, any questions? I'm still optimistic. I'm still doing research because there's so many very hard tasks in NLP to be solved, and the mainstream is kind of bitter, but the rest, like niche domains, are still hard. So let's go back to the evolution of GPT, just to put things in context. So the GPT-1. So we had this transformer encoder-decoder model from Attention is All You Need from Vasvanes et al. And then what came later was the GPT-1 model here in this paper. Was it OpenAI? I guess it was OpenAI people, yeah. Liu et al. And they coined this term GPT in this paper, generating Wikipedia by summarizing long sequences, excuse me. And what they say, like dropping the encoder, okay, so they drop the encoder, doesn't matter, and using only the decoder that consumes input and produces output, trained as a standard language model for writing Wikipedia pages as summarization task. Okay, cool. So they use the architecture of the transformer. They drop the encoder, just decoder for generating text, and they tried it on, writing Wikipedia pages as summarization. So I think they get data from Wikipedia. So Wikipedia was a great source. There's a table with 3 billion parameters. Tokens, and oh no, okay. So this is like precursor. So this, okay, this is interesting. So these people first just used the decoder only in this paper, and then later it was taken by these people from OpenAI, this time from OpenAI. So Ilyas Sustkever and Alex Bradford and others, and they adapted the decoder-only transformer. So they took the idea from the previous research on Wikipedia, and again pre-trained as language model. The pre-train, okay, so the pre-training was just on book corpus. It's interesting. So 7,000 unique unpublished books. It looks very small. So, but you can use, who said books? You were books, articles? Nobody said books. So you can take books. And they pre-trained the model, but then also they did this so-called fine-tuning with an extra final layer for the given task. So the given task would be, okay, so for, summarization, here's the input data and output data. For classification, here's the input data, output data. So they would train the GPT model on this task, but it was already pre-trained, just using language modeling on boot corpus. Something like in BERT model, it was pre-trained on Wikipedia and others, and then fine-tuned for several different tasks. And the size was 12 decoder layers, so 12 attention heads. It's not really important, but it's like the size. And they improved state-of-the-art on 9 of the 12 data sets we study. Cool. I don't know, it was like, I don't remember this paper doing like that many big waves back then, GPT-1. Nobody really cared much, but was there. It was an evolution. What changed was GPT-2. GPT-2 was like a blast for everybody in NLP, like, wow. Okay, so what's changed from GPT-1? It's just larger. It's just a bigger model. That's it. Like 48 decoder layers. Okay, so now going from 12 to 48. The embedding size from 768 to 1600. Okay, so they scale 1.5 billion parameters. It's a huge thing, or it was a huge thing still. It's a big thing. Now you can take GPT-2. And so what happened here with GPT-2 also is, before I go to the details here, is they published the weights. They published the trained model. So they trained the model and they published the weights. So you can download GPT-2 pre-trained, like the weights of the model, and you can just run inference, or you can fine-tune it and so on, which is super, super important for doing research, because you don't have to train it on your, you don't have to train on your own because you don't have the capacities of training your model. So GPT-2 was still open AI, open in terms like, in a way of like research. There's a technical paper, so this technical report, there's a couple of details, not much on the architecture, but the architecture doesn't matter because it was still the transformer decoder only model. But there was like, okay, data sets, something about the training data, pre-training data, not exactly publishing the pre-training data, but still something about them. So yeah. And what they did, they scraped the internet. So they wrote a custom web scraper. But where did they get so you don't want to just scrape the internet by randomly going to sites. So they took Reddit. Everybody knows what Reddit is. And the Reddit has supposedly something like karma points. So I guess like thumbs up or something like that. So if somebody gives you a karma point for a Reddit post, it means it's helpful. Is it something like that? Or it's not trash. I mean, if you got like a couple of karma points, it means a couple of people read this post and kind of agree or whatever. But it means, you filter out some sort of little bit of quality. So if you have a post with links somewhere and somebody gives you a like or whatever, which means like it's not completely spam or lorem ipsum or things. There might be something useful or higher quality than just the general trash on the internet. And they use this. It's a very clever way of getting somehow human check data or links, and they scrape the outbound links from Reddit. So 8 million documents total. It's not much, but well, why not? 8 million. Just thinking about it. I mean, I'm thinking about this. Like, is it 8 million? What could it be? It's much more than Wikipedia, I guess. Yeah, absolutely. I mean, Wikipedia has more sites, right? More pages. So it's a decent size. Was a decent size. It's pre-trained on this web scrape and has some issues because it's web data as compared to books. Books are nicer, maybe. So but it kind of the research after GPT-2 really flourished because you can use this model and do fine tuning, look into the bias of the data because the model is biased because the original data is biased and the bias is transferred into bias in terms of like social bias. So prejudice against minorities, gender bias, and all these things. So people have done research on this. And privacy, so the GPT-2 remembers training data, and you can just get it from the model back and things like that. It's really cool, So the GPT-2 is still there. And I guess one of these videos from Andrej Karpathy building NanoGPT is that just basically loading GPT-2 and getting the weights to work in your model. So very cool model, GPT-2. It changed later with GPT-3, where they kind of dropped the open from the name. Because there is a GPT-3 technical report, but you have no idea what they trained on because they started making money. Anyway, so far so good. Let's go back back and to the future as well. Something has changed with GPT-3. Something has changed with GPT-3 in the world how we perceive NLP and how we perceive tasks. And the thing is called in-context learning. And it's it's still a puzzle. And it's an area of active research. But what in-context learning means. So I'm citing here from one of the newer papers on in-context learning, where they try to kind of understand what in-context learning means. But I found this definition of in-context learning quite nice. So in-context learning is the ability of a model to use inputs at inference time. So what is an inference time, by the way? What is inference time? What do you mean? Yeah, after training, you have deployed the model and it's doing inference. So it's hosted somewhere maybe, or you have it and you don't train anymore. So inference time, we just use the model as trained to use input at inference time to adapt the behavior of the model without weight updates. So we are not doing any weight updates. We are not doing any backprop. We are not changing the weights of the model. The model stays as it is. But we can adapt the behavior of the model in order to solve tasks which were not present during training. So this is pretty cool. We have a trained model. We train it on GPUs. It had some weights. It's big. And then we deploy it in inference. And we can tell the model somehow, and exactly prompt the model, to solve tasks which haven't been in the training data. And we can give the model examples how to solve this task. And the model will adapt its behavior to solve this task without updating the weights. Just basically it's in the prompt. Now for us, it's kind of a daily basis. I mean, it's how we use language models. We give a couple of examples, and then ChatGPT gives us back what it does. But it started something with GPT-3, this kind of paradigm shift, I would say. So GPT-3, which is this paper, we'll get to that in the next slide, first observed that a transform-based language model, back then GPT-3, trained autoregressively. So what is autoregressive training? What do you mean by that? So this is the next token prediction. So autoregressive means it's eating its own input basically while generating. It's basically next token prediction. So autoregressively at what is important here? Sufficient scale, because I will see later GPT-3 was bigger than GPT-2, obviously. And the scale matters. And with the scale came to life this kind of in-context learning thing. And it's still it's unclear why and how exactly, but it happened. So it exhibited in-context learning without any specific effort of the authors to promote it via the training objective for data. So they just train on language modeling. They just train language modeling as GPT-1, GPT-2, just bigger internet, bigger models. And then they observed like, oh, I can tell the model actually to perform task by giving an example. And the task is new. It hasn't been seen in the training data. And the model will adapt to this task just by using this context. It's kind of cool. It's really cool. So what does it mean? Here's an example. So this is from the report on GPT-3. So the standard fine-tuning. So the standard, we don't know nothing in context learning. So standard fine-tuning. So the model is maybe pre-trained and then is trained via gradient updates using a large corpus of example tasks. So what is fine-tuning? Well, I have a pre-trained model on language and then I say I want to fine-tune it on sentiment analysis on IMDb. So I take the IMDb data and then, or maybe here's a machine translation. So I want to train in a machine translation. I have these examples, see other. Anybody speaks French here? Can you pronounce this thing? Because it's very embarrassing if I try. L'outre de mer. Yeah, okay, so you speak French?
No, but I know how to pronounce.
How do you pronounce l'outre de mer? Okay. So let's see other, so we give examples. You know? So, and then after each example or a batch of examples, you do what? Compute the loss, do the backprop, update the weights. Next example, standard SGD. So next is peppermint, which is menthe poivreux. It sounds very romantic. French is very romantic if you don't know it. Menthe poivreux and plush giraffe. Giraffe peluche. I like that. Giraffe peluche, I guess. Pardon my French. Giraffe peluche and so on. So, and then after you finish the pre-training, you get the new task, which is the prompt saying, okay, cheese translate to fromage. I think everybody speaks French here. Good. So this is the standard fine-tuning. So this is how people had been doing task adaptation on these models. Well, okay. But in GPT-3, what I observed is that you can actually try in-context learning in a couple of settings. The most kind of very cool one, the coolest one actually, is so-called zero shot. Why is it called zero shot? It's interesting. So because there is a zero shot, there is one shot, and there is few shot. So I think like the most important, to me, how I understand is like one shot means if you have one shot, you have one trial, one chance. You know, like in the saying in English, do you want to give it a shot? So you have one chance to try something. So let's start with one shot. Okay, so in one shot, you tell the model, so the model is pre-trained, you tell the model in the prompt, translate the task, translate English to French, and you give it just one example here in context. So you give it one example of the task, how to solve it. See other l'outre mer, and then you start with cheese and fromage. So you give the model just one chance to know what your task is about, and the model should pick up what the task is about and how to solve it. And you give just one example, just one shot. If this works, this is already like mind-blowing. You just give one example, like dear model, solve me this, and this is how it looks. And you should learn the task. I don't give you anything else. Of course, you can do more tasks like few-shot learning. So you start with the task description and you give a couple of examples here. But this is everything is just one single prompt. Like you don't do any gradient updates. This is basically just in the context learning. You write this into the prompt. You give these examples as text into the prompt because everything is text to text. So few-shot learning, and of course, the more shots, then the assumption is, of course, I mean, if you give the model more examples from the task, it will have better chances maybe to learn the task. So few-shot makes sense. One shot is kind of, okay, just one example. And the most mind-blowing thing like zero shot. You don't tell the model what to do at all. I mean, you don't tell the model how the task looks like or an example. You just tell the model what to do. Just translate English to French. Dear ChatGPT, write me a reference letter for my PhD application. Zero shot. So, what do you think? Does it work? Well, it works. So it works, of course. But how well it works, it's really mind-blowing. before we get to the results, so pre-training data. So how do they, oh, actually they said something about pre-training data for GPT-3. Okay, so the GPT-4 technical report is the worst one. GPT-3 was somehow okay. They didn't publish GPT-3 weights anymore, but at least they reported something, what they pre-trained the model on. So, Common Crawl, 400 billion tokens. Okay, that's good, that's big. Then books, Wikipedia, okay, here it is. So 3 billion tokens from Wikipedia. So if you compare Wikipedia to the internet, it's actually pretty big. I mean, if you think about it, 3 billion versus 3 versus 400, almost 1% of the internet here, it could be Wikipedia texts. Not bad. I think it's because of the quality, because they filter the common crawl. If you filter, bad stuff from the internet, there's not much, remaining. Okay. So this is the data. They pre-trained the model and then some parameters, because training these big things, you have to make decisions and design choices and things like that. It's really black art in a way. But let's have a look at the results. So, okay, so this is, what is it? They have a couple of parameters of the language model. So this is the X scale. Oh, interesting. So 175 billion tokens is the biggest GPT-3 model. And they also try different sizes of the model. Yeah, that's interesting. So we have 13 billion model, 6.7 billion model, 2 point, and so on. So you have different sizes of the model. And then here, there's accuracy of this task, trivia, question answering. So one of those tasks they were testing on, and there were multiple ones, but I just want to highlight this on this trivia question answering task. So if you fine-tune the model, which is state-of-the-art, you get something like 60-something%. Good. So now let's start with the smallest models. Well, they're just horrible. Was it like 0 shot, 1 shot, and few shot, where few, who says what's few? 64. Okay, if few is 64, I would say like it's a couple of dozen shot, but there is no such a term, so it's called few shot, and few means like a parameter. So 64 shot, and 1 shot and 0 shot. If you start with smaller models, of course, I mean, the only chance you can do something meaningful about this task is using some examples, few shot. And it's still, of course, I mean, all these models, the orange one, it's still better than the others, because you're just giving more information. Of course, the model will learn. What is interesting here is looking at the x-axis here. So if you have the biggest model, and look at the 0-shot learning, which means no example, just tell the task what to do. And compare to, not to the state-of-the-art fine-tune, but compare to other models, smaller models, which have the 64 examples, this is higher. So scale matters. If you have bigger model, pre-train larger, you don't even have to write examples for the few-shot learning. The model will understand what you want to do without showing examples. Or just 1 shot is even better. Just 1 example is just super. And if you do more, of course, you even surpass the state-of-the-art with fine-tuning. So it's cool. Like the bigger model is, the capabilities of in-context learning are mind-blowing. I mean, and the scale matters here, of course. I mean, it's a like 200 billion parameters. It's a beast. It's a huge model, but it looks like a little bit linear. Like, I mean, what happens if you had like 300 billion models? Yes. Is it exponential? Is it logarithmic? Okay. Yeah, it's sort of, yeah. It's very bad because there is no scale. It could be log. It could be log. Could be log. Somewhat. So here we would have like 1 trillion parameters, maybe something like that. So if you have 1 trillion parameters, where does it stop? No, this is, I mean, nobody knows. I mean, we don't know. There is a research on so-called the scaling laws of LLMs. And they try to predict if you scale up the model, what will happen with the task? Like, is there a law? Because this looks like an exponential growth. What are the properties of this? Can we predict this? Yes.
I think the newest NVIDIA graphic cards also have these tensor cores, which are optimized for learning. Were these cores already used for training GPT-3, or are they used for training GPT-4? And is it expected that there will be a higher or better models coming soon if these cores are used?
Which cores in? So I don't know. I'm not a hardware guy, but what are the cores in no, which cards? So which card?
Very new, extremely expensive media cards that they have.
Well, to me, like all of them are very new and very expensive. Like if you have to pay them, I don't know. So if you have I mean, yes.
Last two generations, and essentially what they do is they are only optimized for matrix multiplication, so they strip all of the graphic.
Yeah, exactly. Yes. I mean, if you buy the standard GPUs used for these training were A100s 80 gigs, H100 80 gigs, and H200 80 gigs. These are the biggest beasts you can buy today or a year ago. There's always something new coming from NVIDIA. The bigger the merrier. It's very expensive. For example, buying a server with 4 H200 GPUs, 80 gigs is 160K, and it's very cheap. So I'm looking forward to this. I just bought it. We just ordered it for the research group. So I'm curious, and you don't want to do this on your RTX 4 or 07 or whatever. You can. I mean, you can train small models. If you have like 12 gigs, 16 gigs, you can train small models, of course. That's fine. But you should use it for gaming. Actually, I tried. I bought a GPU for home, and I thought like I'm gonna do some deep learning, and I ended up just trying Steam. I shouldn't record this on YouTube, but anyway, that's true. It's been a while. I was gaming for the last time, so I gave it a shot. It looks great. Okay, but back to deep learning. So these were I think they were trained on the standard GPUs like A100s, thousands of them. And if you read the news like NVIDIA, and there's a shortage in graphic cards, that's because the biggest players are buying them. That's right. And there's one thing, so Google has these Tensor TPUs, so maybe Google is training on their own TPU architectures, but the standard, standard industry things is just GPUs. Okay, so I don't remember the question exactly, but what's the future? Who knows? I'm not a hardware guy, so there are better sources for this information. But the scaling loss is a thing. So this was one example. Another one, superglue. So the superglue is a combined benchmark of different data sets for general language understanding evaluation, it's called, I guess. And again, scale matters, random guessing, kind of at the beginning, zero shot has no chance. It's even worse than random guessing. Wondering why. Well, anyways, it's just wrong. And then it gets better, and maybe on this superglue it's kind of hard task, so you cannot really compete with BERT fine-tune and human language or SOTA, state-of-the-art fine-tune. But still, even like one shot is good. If you can give one example, you're matching here fine-tune BERT large language model. Why is it cool? So if you have these results, you fine-tune BERT large, and then you have big model and then just give one shot. Why does it matter? Because for fine-tuning BERT on a task, you need a GPU, you really need to train this thing for a long time. Here, this is inference time. Like this is inference time. You have the model running and you just write, translate this English to French, here's one example, period. And the model knows what to do, and it can compete with fine-tuned models. So this is the beauty of in-context learning. You don't have to train these models. And actually, you don't want to train, you even cannot train these models. Some of these models you cannot train because you physically don't have access to the weights of the model, or you don't just have the hardware to train these models. Like you don't want to fine-tune Llama, for example. I'll get to that. Okay. So here's something which is now kind of a little bit obsolete. But they did a study, which was kind of cool. Generating plausible news articles, and they ask humans whether they can distinguish between whether the article was written by a human or GPT-3, and guess what? 50%. So people weren't unable to distinguish that. Now we know why. Of course, now Can you distinguish something written by ChatGPT or a human? Ken?
I think sometimes I have read so many GPT answers that I kind of see a pattern.
That's interesting, right? Yes. There is something like you have a sense of something. I can definitely see it on emails like I'm getting from students and applications for PhD. I see, okay, good. I have to skip this because it's ChatGPT. I'm saying like, why do you write this? I mean, I don't even read it. So of course, and sometimes, yeah, I can spot it in master's thesis. So warning, if I'm looking for master's thesis students, and I'm looking for student research assistants. I'll do the announcement on Moodle and on Discord, but I'm interested in, I'll be hiring like student research assistants because these are paid positions. So I think I'm gonna do like 4 at least. And master students, yeah, I have some cool tasks to be done. So. But then, warning here, I can spot if you write your master's thesis with ChatGPT, I just need two paragraphs and I will know. Okay. So what I'm saying, my students now, write your thesis just by writing. Come on, just write this bloody thing. Nobody want to read like ChatGPT thing. Anyway, because we know you have on average, depending on the domain, you have no chance. So I wish some texts were written by ChatGPT. For example, official letters from some bureaucratic stuff. Yes?
I'm not too sure on the name of the study, but there was a study conducted on how much of new research is generated by AI, and they found that actually a staggering amount of 80%. And sometimes in some, even in some, that they contain text generated by ChatGPT. And sometimes you could even find in the abstract the prompts.
Yeah, sure. Yes. There are instances of accepted papers saying like, oh, I'm a language, somewhere in the text, like, oh, sorry, I can't help you. I'm just a large language model. I cannot help you with this task. And it end up in the research paper. Yeah, not all research is equal, I can guarantee you. Not even like in the top conferences. And so for example, at ACL, family of conferences, that there's also like issue, not even the papers. I wouldn't care about the papers because it doesn't matter how it's written. What matters is like the method or, results or something like interesting. Is there interest? Is it interesting enough? Then you don't really care how it's written. And sometimes even better, people use ChatGPT to polish this because if they don't, like, it's full of typos and errors. It's like, Jesus, come on, like, no. So it's okay. But reviews of these papers written by ChatGPT, yeah, it's bad. People are using this, unfortunately. If you are a reviewer for these conferences, you shouldn't use that. And there's some ethical statement you need to adhere to. So, but you cannot enforce it. And it's a big issue. And I don't think we have a principled solution because it's out there. Like everybody can use this for everything. So we have to be wise in the future what to do with our society. Which comes more into maybe we should have a lecture on like ethical NLP. Maybe next week. Let's talk about it later, but let's finish this GPT thing. So now it's not any news, but back then, oh wow, it can really generate text, I can understand. It's really like mind-blowing. But the ICL was really. So why does in-context learning work? It's an active area of research. Like, why does it work? So here's an example. Maybe it's old now because it's 2022. We have 2025. Maybe it's not state of the art anymore. So they tried something here. Okay, let's skip these details. This is just an active area of research. There's so many things going on. Some people are very crazy about it, like transformer attention has a dual form of gradient descent. So you're trying to understand. So I just looked it up yesterday. There's one survey paper about research on in-context learning published at this year ACL, and they surveyed about at least 30 papers which try to explain why in-context learning works. So I'm not going to highlight any of those because the jury is out. Nobody really knows exactly. This paper I mentioned here from this team, they took also one approach, PAC Bayesian learning, whatever it means. So PAC learning, and they try to explain how it works and why. But the takeaways here for in-context learning. So we don't know why it works. We don't even maybe know like how it works. We know how fine-tuning models work, like intrinsically, like on the mechanical level, but the why question, like why this picks up, is it just because of the scale? Because the in-context learning has something to do with the scale. In-context learning will appear only if you scale to certain size and number of input which you pre-train on. For smaller models and smaller data, in-context learning is not there. And somehow it will appear after you train for long and bigger models. And it's active area of research, like, why is it a rule there? What happens? Where's the transition where it starts to appearing? Like, why these models can do in-context learning? Where does it start? Scale, data, who knows? So, who knows? But why is it cool? So the GPT-3 paper and then everything in context learning show that non-trivial alternative to fine-tuning emerges. So it's called emergent capabilities also. When large language model is large enough. LM can be specialized to downstream NLP tasks by simply receiving its input and a string composed of concatenated training examples of this task. So this is it. And the weights are unchanged in this procedure, but there is some form of learning. It's evidently taking place. If you show it 64 examples in the prompt, it will learn the task. Why the heck? So the performance significantly improves with the number of concatenated training examples. Yeah, of course. So zero shot versus one shot versus many shot for this disparate variety of NLP tasks. So the takeaways are, yes.
So if I include more examples where I want to do it, my ChatGPT prompt, it would give me probably better results.
Yeah. I guess. I don't know ChatGPT that much, like on the practical level. In general, yes. This is like, in general, transformers, yes. So it has a profound practical impact on the applicability of large LMS because we don't have to access the model weights in order to specialize the model for a certain task. And often, we don't need so many examples, actually. This is pretty cool. So I have a couple of slides left, but maybe let's keep it for next time. It will be short. Or, yes?
Will you also tell something about the research you're doing?
What my research is doing?
Yeah.
Oh. So we can plan next semester for it. No, I'm kidding. So, okay, let me think whether we should finish this today. Alignment, okay, no. Let's keep it for, because I guess we should meet maybe next time, or maybe it's super important. Let me just stop first recording.